Thank you, Katya. Okay, so let me start by thanking Katya for the invitation to this lovely webinar series and also to the audience for listening. So this is based on a joint work with Lauri Oksanen, and basically I will focus on these kinds of ray transforms that we discovered with Lauri when we were studying some inverse problems for nonlinear PDEs. And these ray transforms are essentially some weighted transforms along either geodesics or null geodesics with weights that depend on Jacobi fields along the ray. And they have some nice distinctive features compared to classical X-ray transforms. For instance, and this is perhaps the main message of this talk, is that these transforms can be inverted along a single ray. So they are very suitable, for example, for partial data problems. So I will, along the way, give relations to inverse problems, and I will essentially spend a few slides just to make a connection between PDEs and these transforms. And then I will discuss some invertibility results that we have with Lauri along a single ray. Okay, so let me start with the motivation of this talk. And to do this, we start with considering a smooth manifold, a smooth compact manifold with a smooth boundary. And then we assume that we have either a Lorentzian or a Riemannian metric G on this manifold. And then we consider the set A, which is basically the set of smooth functions on this manifold that solve Laplacian U equals 0. So basically, in the Riemannian case, this would be a smooth harmonic functions on the manifold. And in the case of Lorentzian metric, this would be a smooth waves. Okay, so basically, we are really interested in this question in analysis, which is if we take a product of M elements of the set A, is this set going to be a complete set? So more specifically, if we fix some M bigger than or equal to 2, and if we have a continuous function that integrates to 0 against any product of M elements in the set A, does it follow that this function Q must be identically 0? So this question, in fact, has lots of applications to inverse problems, specifically for linear or nonlinear PDEs. And I will make some of these connections along the way. But I would say that this is also a very interesting question in analysis in its own right. So we want to really focus on this question. And basically now, in the case that M is 1, so you just have one element of the set A, this is obviously false. But in the case that you have products of 2 or more solutions, this is believed to be true. So what I would say is that basically this question has been studied a lot in the case that M is equal to 2. It has also been studied recently in many works when M is bigger than or equal to 4. But as far as I know, there have been no works that focus on products of exactly 3 solutions. So this particular case, M is equal to 3, is what I will be focusing on. Okay, having said that, let me mention some of the previous results in the case that M is equal to 2 or M is bigger than or equal to 4. And I will start with the M is equal to 2 case on Lorentzian manifolds. So again, the question is, if you have 2 waves on if you consider product of 2 waves on Lorentzian manifolds, does this form a complete set? Now, this question has lots of applications in Calderon type inverse problems for linear equations. And I would say that if you can solve this question, if you can show this completeness, then you are in very good shape of recovering lower order coefficients from boundary data for general second order hyperbolic or elliptic PDEs. So in the context of inverse problems, this is a very important question. Now, specifically in this Lorentzian setting, basically you can use geometric optic rays or Gaussian beams or propagation of singularities to show that in the context of very general Lorentzian manifolds, this completeness question can be reduced to the question of injectivity of the so-called light ray transform of Q, which is basically the integrals of Q over affine parametrizations of null geodesics, and where a null geodesic is just a geodesic in your space-time with the additional restriction that the tangent must be known. Okay, so this reduction for this question can be done in very general Lorentzian manifolds, but unfortunately, inversion results for this light ray transform are quite scarce. So basically what is known is that, for example, if your manifold has a real analytic atlas, and if your metric is real analytic, and if additionally your manifold satisfies some convex foliation property, then this light ray transform is injective. This is a result by Stefanov. And injectivity is also known if the manifold is a stationary Lorentzian manifold that satisfies a certain convexity condition. This is joint work with Ilma Birta and Oksana. Here, by stationary, I mean that there exists a smooth time-like Killing vector field on your manifold. So basically, you can see that this light ray transform, its inversion is known either under some real analyticity assumptions or under some symmetry assumptions. Okay, so next I move to the basically Riemannian setting for this product of two solutions or two harmonic functions. Does this set form a complete set? And I will first focus on Euclidean domains because this is very well understood. So this is basically the original paper of Calderon, where he proved completeness on this set A of product of two elements of this set A by introducing these complex geometric optics, which are harmonic functions of the form e to the I zeta dot x, where zeta is a complex vector that is orthogonal to itself. So actually, these family of harmonic functions form a complete set. But actually, in Euclidean space, we could say something much stronger, which is a result by Dos Santos Pereira, Koenig, Schostrand, and Ullmann, namely that even if you restrict the traces of harmonic functions to vanish on arbitrary open subsets of the boundary, so if you look at this set B, again, product of two harmonic functions in this set B would form a complete set. Okay, so basically the Euclidean picture is quite well understood. What about the Riemannian setting if you have product of two harmonic functions? Well, right away, I have to impose some very strong assumption. And this is just because I would say nobody knows what to say for more general Riemannian manifolds. So the assumption that I will impose is that we have to work with these conformally transversally anisotropic manifolds, which were introduced by Dos Santos Pereira, Koenig, Salo, and Ullmann. So these are manifolds that topologically, basically, they can be embedded in this kind of cylinders, R cross M0. And additionally, the metric conformally admits this orthogonal splitting. So basically, modulo this conformal factor, you have this Euclidean direction in the manifold. So basically, I will focus on these CTA manifolds throughout the talk whenever I mention Riemannian manifolds. Okay, so what kind of results do we have if you have product of two solutions? Well, first, if you assume that this conformal factor is identical to 1, and if you assume that the transversal manifold is real analytic, and there is some additional mild assumption about intersecting geodesics, then completeness is known. This is a recent result by Kupchik, Limatinen, and Salo, using analytic wavefront sets and Gaussian Quasimodes with exponential bounds on the correction terms. But if you want to say anything about completeness without real analyticity properties on the transversal manifold, then what is known is basically the following fact, that first of all, you can use fairly general Gaussian Quasimode constructions to reduce this completeness question to the study of injectivity of the geodesic ray transform on the transversal manifold. This is basically a result by Ferreira, Kurilev, Lassas, and Salo that basically says if the geodesic ray transform is injective, then you have this completeness for product of two solutions. Now, injectivity of the geodesic ray transform, I mentioned perhaps the two most famous results. or settings where this injectivity is known. One is that the transversal manifold is simple, so the boundary is strictly convex and there are no conjugate pair of points. This is due to Mohometov and basically is based on energy estimates and the test of identities. There is also the situation where the manifold has a strictly convex boundary and admits a foliation by a strictly convex hypersurfaces. So this is a result of Ullmann and Vajy using scattering calculus of Melrose. Okay, so this is what I wanted to say about product of two solutions, either harmonic functions or waves. What happens if you have product of four or more solutions? Well, let me first give a connection to inverse problems. And to do this, let's consider the following Cauchy data set, which is the traces of u and the normal derivative of u on the boundary of your manifold, where u is a smooth function that solves these kind of semi-linear PDEs, where the principal term is this Laplacian, but then you have this semi-linear function depending on the solution. And you assume typically that this semi-linear function is analytic with respect to the solution u. So it has this power series expansion. And then the inverse problem would be to determine these kind of nonlinearities from this Cauchy data set on the boundary. Okay, so basically, if we go back to the work of Kurilev, Lassos, Ullmann, that considered Einstein equations, they introduced this idea of this multiple fold linearization. And this idea that was introduced in that paper can be used to study these kind of inverse problems with these semi-linear nonlinearities. And so basically, there are lots of results addressing these kind of inverse problems. And I've mentioned a few here, but I apologize if I've left others out. So basically, for instance, in the work of Kurilev, Lassos, and Ullmann, these kind of inverse problems are considered with a quadratic nonlinearity, and the aim is to recover the metric. Lassos, Ullmann, and Bank considers these similar kind of problems, and they are interested in recovering the metric and the nonlinearity. But these two works, these two first works are based on, I would say, more complex interactions of singularities or more complex interactions of linearized solutions. So completeness of products of solutions do not clearly appear in these two works. Then with Oksanen, we consider the question of recovering like the first order term if you have a k equals 1 in this expansion and we want to recover v1. And Hinz and Ullmann and Jai consider a similar problem on manifolds with boundary, and they want to consider recovering these coefficients vk with k bigger than or equal to 2. And basically, as far as completeness of products of 4 or more solutions go, these appear, for example, implicitly in these last two works. So basically, products of 4 or more waves forms a complete set in very general Lorentzian manifold. Now, what about the Riemannian setting? Okay, so in Riemannian setting on CTA manifolds, again, these kind of inverse problems have been studied starting from these two works, Lassos, Limaten, and Lin and Salo, and myself and Oksanen, that came out at the same time. And there have been few results since then that, for example, consider partial data versions for different kinds of nonlinearities. And as far as completeness of products of 4 harmonic functions on CTA manifolds goes, this is something that, for example, Mati, Tony, Yishon, and Nico proved for very general CTA manifolds under absolutely no assumptions on the transversal manifold. We also proved with Lauri's completeness result for product of 4 harmonic functions on CTA manifolds, but we imposed some mild assumptions on the transversal manifold. Okay, so this sort of concludes my review, and I want to now focus on this setting where we have product of exactly 3 solutions and see what we can say. Okay, so basically, let me start with this Riemannian setting. Let me focus on this. So we have product of 3 harmonic functions on CTA manifolds. And so basically, this means that we have a manifold. Again, recall that the manifold has this embedding, and the metric admits this kind of a splitting. And for simplicity, let me just take this C to be 1. This is not really important, but it makes some of the stuff that I'm going to talk about easier. So the metric is just dt squared plus G0x. Okay, so on these kind of CTA manifolds, what is nice is that you can construct lots and lots of harmonic functions that concentrate on certain planes. And these planes are basically planes that are spanned by the Euclidean direction in the manifold, here denoted by this T, cross geodesics in the transversal manifold. And let me say that these geodesics could be very general. So they could have conjugate points and they could have self-intersection. But basically, no matter what, you can construct these kind of harmonic functions that concentrate on these planes. And what I mean here is that there will be some exponential growth in the t direction for these harmonic functions. There will be high oscillatory terms along the geodesic, but then there will be a Gaussian profile of decay away from this plane. So in this kind of y directions. So this is a construction that was carried out on these CTA manifolds by Dos Santos Pereira, Kurilev, Lasas, and Salo. And they are quite similar to Gaussian beam constructions on Lorentzian manifolds. So now let me give the forms of these Gaussian Quasimodes. And to do this, let me use a good coordinate system. So I will use the Fermi coordinate system around the geodesic. So this would be the RY coordinate system, with this R denoting the arc length parameter along the geodesic, and then these Y coordinates being a suitable transversal coordinates to the geodesic. And then, of course, we have the T, which is the Euclidean direction. And the geodesic can be parameterized as R, 0 in these Fermi coordinates. Okay, so using these Fermi coordinates, we can precisely give a very simple expansion for these Gaussian Quasimodes, which I denote by capital U lambda. And here this lambda is a complex parameter. So it's basically tau plus I sigma, with this tau some very large positive real number. And this sigma just some offset in this parameter lambda. So there is some bit of imaginary. So there is an imaginary bit in this lambda. And then what the Gaussian Quasimodes look like, they are of this form, where as you can see, there is this exponential growth that I spoke about earlier along the t direction. Then there is these highly oscillatory terms along the geodesic. And then there is this Gaussian profile of decay away from, so in these y directions, which is basically away from the plane t cross r. And this Gaussian profile of decay can be guaranteed as long as you impose that the imaginary part of this matrix is positive. So this H is basically an n minus, if your dimension is n, this is an n minus 2 by n minus 2 matrix. And then there are some leftover bits in terms of power series in the transversal coordinates that don't really matter. And then there is an amplitude term that appears here, and this amplitude has this principal term, which is the determinant of some n minus 2 by n minus 2 matrix along the geodesic to the power of -1/2 times the cutoff in the transversal directions. And then finally, there is a correction term, which is quite a small in terms of Lau, and we have quantitative bounds on this R lambda in terms of powers of 1/λ. And then there is also another family of Quasimodes that only change insofar as the direction of growth changes, so it becomes the opposite. And then the oscillations, you see the conjugate. So basically the oscillations also change, but the rest is more or less the same. And so as you can see, to understand these Gaussian Quasimodes on a principal level, all you need to do is to understand these matrices H and Y that appear in this construction. And there is actually a very nice geometric description of these. I would give, for example, the following two references. So in the case of geodesics, this appears in the book of Dahl. And also for Lorentzian manifolds, if you consider Gaussian beams, you will have the similar kind of constructions with similar matrices appearing, and you can look at these geometrical interpretations in the book of Caccialo, Kurilev, and Lassas. So what basically happens is that if you do change of coordinates, you realize that this h and y are really 1-1 tensors on the transversal manifold, on the transversal planes gamma dot perp, which is basically tangent planes in the tangent space that are orthogonal to gamma dots. So basically these 1-1 tensors h and y live in these n-2 dimensional planes. And basically h is given by the following equation in terms of y. So it's basically the derivative of logarithm of y. And the y matrix or the y tensor solves the following complex Jacobi equation. So the second covariant derivative along the geodesic minus ky equals 0, where k is the 1-1 Ricci curvature tensor. Now, of course, because you have these 1-1 tensors, this product makes sense. And you have this equation. But if you want to even have a better geometric intuition, let me just say that if you fix some coordinates for these tensors, then the columns of the tensor y will be Jacobi fields along the geodesic. So they will be transverse, actually, Jacobi fields along the geodesic. Okay, so there is one condition that you need to impose on this y. Namely, if you remember, you want a Gaussian profile of decay. So you want this matrix H here to, first of all, be symmetric and also to have a positive imaginary part. So this is the condition that I've imposed here. So you need this matrix to be symmetric at one of the points along the geodesic. And you also need the imaginary part to be positive at some point along the geodesic. And the interesting fact is that as soon as you impose this condition at one point along the geodesic, it will propagate to all points along the geodesic. This is somehow a conserved property because because these tensors are solving this second order ODE. Okay, so this is a condition that we have to use. Okay, so this is the review of Gaussian Quasimodes with the geometric interpretation of this y and h. And let me just point a remark here. So suppose you want to consider product of two harmonic functions. Well, you can immediately see that if you have to work, first of all, with the same geodesic to get rid of these bad terms. And then what you have to do is to consider this u and multiply it with this u tilde, because that gets rid of these exponential terms, and it will get rid of these high oscillations, and then you can do some stationary phase along the geodesic. If you have product of four harmonic functions, then you can do lots of things, but one very good thing you can do is to take two intersecting geodesics and then take u and u tilde along one geodesic, and then you can use the same two quasimodes along the second geodesic, and then you again see that these oscillatory parts and the exponential parts cancel out, and you are only left with these good Gaussian decays. And so you see that at least locally, you are in with a shot of concentrating information at the point of intersection. So this is, for example, the approach that on CTA manifolds, Mati, Tony, Yishon, and Nico use. Of course, they have to also handle the other intersection points, but they can do that with some clever tricks with this imaginary part of the frequency lambda. Okay, but what happens if you have three harmonic functions? Can you use intersecting geodesics to study completeness? And basically, I want to show it to you that you can't. So I want to show that you have to work with the same geodesic. And the reason is that, okay, so let's take three geodesics and let's take the point of intersection P, and let's look at the tangent vectors C1, C2, and C3. Then your Gaussian, and let's take a normal coordinate system at this point of intersection. So then basically, if you look at your Gaussian Quasimodes Uj, lambda j, along the geodesics gamma j, then you see that up to principal parts, so up to this exponential term and the high oscillations, this is what your Gaussian Quasimode looks like. near the point P. So basically, modulo this amplitude, it looks like CGO solution that was introduced by Calderon. And here, so these tau j's are the real part of lambda j, and these CJs are basically the tangent vectors to the geodesic at the point P, and they have to be like unit vectors. So CJ dot CJ has to be 1. Okay, so now if you want to take product of 3 harmonic functions, 3 Gaussian Quasimodes along these geodesics, the only way to have a hope of getting anything at the point P by a stationary phase is for these exponential terms to cancel out completely. So this will give you 2 equations. This will give you an equation for the T part canceling out. So this will, for instance, give you tau 1 like equals tau 2 plus tau 3 or something like this. And then you will also get an equation on the imaginary part canceling out. So this will give you an equation on these tau j's, CJs. But surprisingly, because of triangular inequality, you can show that even though you have all these parameters, tau j's and CJs, because of triangular inequality, the only way that these 3 exponentials can cancel out is that all these CJs must be collinear. And this is something that even if you go to Lorentzian setting and carry out Gaussian beam constructions, you see the same phenomenon happening. So you cannot have 3 Gaussian beams that concentrate on 3 different null geodesics to cancel out at the point P. And this is because if you have 3 null geodesics that are linearly dependent, then those 3 null geodesics have to be basically, those 3 null vectors have to be collinear. Okay, so this is maybe one of the reasons that this product of 3 solutions has a different flavor than a studying product of 4 solutions. Okay, so basically we have to work with the same geodesic. But if we work with the same geodesic, then there are ways of canceling out the bad oscillations and the exponential growth. So namely, you can take the same geodesic, and then you can take for one of your harmonic functions u lambda. For the second harmonic function, you can again pick u lambda. And then for the third harmonic function, you can pick this u tilde 2 lambda. So by choosing these harmonic functions, you will see that the exponential growth in the t directions cancel out. And you will see that the oscillations along the geodesic also cancel out. And you are left with this kind of integral in the manifold being equal to 0 against this function q. And okay, so let me study this. So here you can see that basically all these bad exponentials and the oscillations have canceled out. And the first time that this large parameter tau appears is as a coefficient of this Gaussian. So you can do a stationary phase basically. And then basically you see here we have 2 amplitudes coming from this u lambda, and then we have an amplitude conjugate coming from this u tilde to lambda. So if you multiply these principal amplitudes, you end up with the following expression along this geodesic. So if you want to do a stationary phase here, what really matters is this determinant of the imaginary part of H. And there is actually a very nice identity that relates the determinant of the imaginary part of H to this guy. And basically what you have is that this identity must hold along the geodesic for some constant C positive. So if you do a stationary phase, basically the factor that comes from this determinant of the imaginary part of H completely cancels out with this determinant y absolute value to the power of -1. And then you are just left with this remaining factor. So basically your final identity after you do a stationary phase ends up being the following equation along the geodesic, where here this q hat is the Fourier transform along the t direction. And remember, this sigma is just some fixed leftover frequency, which is some small number, for example. So basically you get the transform of this function along the geodesic with these weights. And these weights, remember, the matrix Y is related to the Jacobi fields. So basically the columns of Y are transverse Jacobi fields along the geodesic that satisfy a conservation law, namely that the imaginary part of y dot y inverse should always be positive along the geodesic. So let me just comment that if we did not have product of three harmonic functions, then this factor will not appear. So we would just get integral of the Fourier transform of Q with this exponential along the geodesic. And so there is no hope of inverting this transform if you just focus on one ray. So then, first of all, you need to consider infinitely many rays, and you also need to know injectivity of the geodesic ray transform to begin with. But basically what happens when you have product of three solutions is that somehow, miraculously, this one ray is enough. You can immediately invert using that single geodesic. So now that you have seen this transform, let me move it to an abstract setting and basically introduce these Jacobi transforms on Riemannian manifolds. So we start with the set of all complex 1-1 Jacobi tensors along geodesics gamma that are normal to gamma dot and additionally satisfy the following conservation law. So this tensor is symmetric at some point on the geodesic, and the imaginary part of this tensor is positive at that point. And again, these y tensors, the columns are basically just Jacobi fields. Okay, so we start with the collection of all such tensors along the geodesic, and then given a real valued function, we define the following transform along the geodesic, which is defined as the integrals of f against that fixed geodesic, but with all these possible ways that are coming from Jacobi fields. Let me just make a remark that here I'm assuming that the function is real valued, but you can always assume this because if you go back to the PDE side here, you can do the same construction, and instead of this, you can work with u tilde lambda squared, u2 lambda. And if you do this, you get the same expression, but with a conjugate here. So basically, you have these transforms, and you have the transforms with the conjugate here. So without loss of generality, you can always assume that the function that you want to invert is real value. Okay, so we have this transform now in an abstract setting, and we want to know if you can invert it along this single geodesic. Let me just say that, so this is on a general Riemannian manifold that I defined this Jacobi weighted transform. If you have a Lorentzian manifold, then you can do the exact same thing. You can consider the same set of Jacobi 1-1 tensors, but you have to consider them along null geodesics as opposed to geodesics, and they have to be normal to the null geodesic. So then you can you can just replace these geodesics with null geodesics and Lorentzian manifolds and consider the same transforms that come from products of three solutions to the wave equation on Lorentzian manifold. Okay, so what are inversion results that we have? Basically, if your manifold is 2 or 3 dimensional, what we can prove with Lowry is that if you have a geodesic, if you have an inextendable geodesic on this 2 or 3 general Riemannian manifold, and if you assume that your geodesic does not have any conjugate points, then this transform can be inverted along that single geodesic. So if you have a function that integrates to 0 against all these weights on that geodesic, then that function must be 0 along that geodesic. You can state, you can basically copy and paste our proofs for the Lorentzian setting, and there would be really no change. So you can obtain the same results for 1+2 and 1+3 dimensional Lorentzian manifolds if you assume that there are no conjugate points along null geodesics. Let me just say that what I mean by no conjugate points along this closed interval is that if you consider an infinitesimal extension of the manifold, then this geodesic should not have any conjugate points on this closed interval I. Okay, so now let me discuss how you want to invert this. And I like to basically sketch this in Euclidean geometry because it gives you a picture, even though maybe right. So anyways, I will focus on the Euclidean case. So in the Euclidean case, what do Jacobi fields look like? They are basically just affine along the geodesic because you get that the second derivative of these tensors are 0. So basically these tensors are just affine tensors on gamma dot curve. So if your Riemannian manifold, if your domain is n-1 by n-1, then you can basically choose any affine matrix along the straight line. And because we can choose lots of matrices like this is one such example. So I will choose these kind of matrices for my y. So they are given by r minus I epsilon for some epsilon positive. And the reason that I impose that this epsilon is positive is because you remember that this y needs to satisfy a condition, namely the imaginary part of y dot times y inverse needs to be positive at some point along the ray. And if you choose this epsilon positive, then you see that this condition is satisfied. Okay, so we can choose all these kind of ways. And if you have a Jacobi transform of a function vanishing for all these y epsilons, then it means that integral of f against determinant of these matrices to the power of -1/2 vanishes. And so basically you obtain the following equation for all epsilon positive. And then one thing that I forgot to mention is that you can assume without loss of generality that 0 is not in this interval where your geodesic is defined, for example. You can do this by a shift of this r. So you can assume that r equals 0 is not in this interval. So then we get that this identity must be satisfied for all epsilon positive. And then you can just take the Taylor series expansion in epsilon and look at the powers of epsilon, and they almost vanish. And this will give you the following equation. So it will give you that this function multiplied by all powers of r to the -1 should vanish along the geodesic. And then, of course, you know that if you take this function r to the -1, its powers form a complete, its powers form a dense set in the space of continuous functions on an interval by Stone-Weierstrass. And so you can conclude that the function f that appears here has to be 0. So you see that the inversion of Jacobi transform in Euclidean space is quite easy along a single ray. And even though this result might look very simple, you can actually use this as building block of interesting results. So this is, for instance, what we used with Katalin Karstea to prove the following result, that if you have a domain in Rn with a smooth boundary, then the set of tensor products of m, the gradient of m harmonic functions forms a complete set. So for m bigger than or equal to 3. So this in all dimensions forms a complete set. And this is useful for inverse problems of certain quasi-linear elliptic equations. In particular, let me say that the case that m is equal to 2 is connected to the linearized Calderon problem. So if you take the original Calderon problem, and instead of taking an isotropic conductivity, if you take an anisotropic conductivity and linearize, then the question of the linearized Calderon problem becomes the question of injectivity of product of 2 of these. And that is not complete because there is a natural gauge. But this result says that if you have more than or equal to 3 products here, then you get a complete set. Okay, so now let me go back to this Jacobi transform on general Riemannian manifolds. And let me go over the proof in the case that your manifold is 2-dimensional. Okay, so again, we start with assuming that we have a function that whose Jacobi transform is 0 along a geodesic, along a fixed geodesic, and we want to show that that function must vanish on that fixed geodesic. So we consider an artificial infinitesimal extension of this manifold M, and we just choose gamma A to be a point that is just sitting outside the manifold on this geodesic. Then, because it's very close to the boundary, and because this geodesic does not have any conjugate points, you can show that there are no points on gamma that are conjugate to gamma A. And then what we do is we consider, so remember in this case that the manifold is two-dimensional, the space of transversal Jacobi fields are just scalars. They are basically just functions. So they are just solving these kind of linear ODEs. So this is just a scalar function whose second derivative minus k times y equals 0. So it's just the Jacobi field. And then for this Jacobi fields, I will take the two fundamental ones. So I will take one to be such that the value of this Jacobi field is 0 at the point A, and whose derivative is 1. And then I will take the second transversal Jacobi field to be such that y2 is equal to 1 at this point A, and whose derivative is 0. So I take the two fundamental ones, and of course, any linear combination of them is a Jacobi field. So in particular, I will take this one. I will take y1 minus I epsilon y2. Again, I impose that this epsilon is positive, and I impose that to make sure that this conservation condition for the Jacobi tensors are valid. Okay, then the Jacobi field of f vanishing along this geodesic implies that this integral must vanish for all matrices y. And in particular, if you put these y epsilons here, which are given by this expression, so there is no determinant here because this is just a function. So if you put these y epsilons here, then you get that integrals of f of r. So basically, you get that this integral now must be 0, where this capital X is now just y2 times y1 inverse, and this f tilde is given by this equation. And the important point is that the no conjugacy assumption on the geodesic implies that this Jacobi field is never going to vanish along the geodesic. So this y1 is always going to be a strictly positive on the interval I, and so this x is always well defined. Okay, so this transform must vanish along the geodesic for all epsilon. So again, you consider Taylor series expansion in epsilon, and all the powers must vanish. And this implies that the following identities hold for all powers of k, 0, 1, 2, and so on. And then, okay, let me be a bit, let me hand wave a bit. So if you do a change of coordinates, so if you call this x of r to be s, then this gives that basically some h, which is related to just change of coordinates here of f tilde, multiplied by s to the k, ds must be equal to 0 for r of k. And then you can just use the Stone-Weierstrass to show that this h must vanish, and so f must vanish. And to make this argument rigorous, what I will show to you is that this change of coordinates can be done, or this change of variables here can be done. And to show that to you, I will show to you that this x is monotone along the geodesic. And to do this, notice that x is given by the following definition. So it's y2 times y1 inverse, where these y2 and y1 are solving second order ODEs. So if you look at the derivative of x, you just get the Wronskian for this ODE times y1 to the power of -2. So of course, this y1 to the power of -2 is always positive along the geodesic. And this Wronskian is just a constant along the geodesic. So in particular, it is equal to its value at the point A, which is equal to -1. So you see that this x dot is always going to be negative. And so this x is monotone. And so you can do this change of variables to apply a Stone-Weierstrass. Okay, so this is basically our proof in the case that you have a two-dimensional Riemannian manifold. On a three-dimensional Riemannian manifold, I would also maybe like to quickly go over the proof because it has a different flavor. So on a three-dimensional Riemannian manifold, again, we have the fact that you have a function, you have a real valued function whose transform on a fixed geodesic against all these kind of weights related to Jacobi fields vanish. And you want to show that f must vanish on this geodesic. And to do this in dimension 3, first note that these matrices Y are 2x2 matrices when your manifold is three-dimensional. So we take a fixed point along the geodesic, P in gamma, and we want to show that F at that point equals 0. So without loss of generality, I'll just write P is gamma 0. So, and then I will consider the following family of Jacobi tensors, y epsilon, which are given by x minus I epsilon z, where now here this x and z are 1, 1 Jacobi matrices living in this gamma dot curve, such that this x at the point 0, so at the point P is 0, and its derivative at the point 0 is identity. And then the tensor z is the opposite. So it is identity at 0, and its derivative at 0 is 0. Now, because this x here is a 2 by 2 matrix, and because there are no points on gamma that are conjugate to P, then you can show that this determinant of this Jacobi matrix will be strictly positive on the entire geodesic away from 0. So this will be very important. So this determinant will be strictly positive. And then we just plug in this y epsilons basically in this equation and see what we can get. So if you do that, okay, if you do that, you get this identity. So here, instead of just y epsilon, I'm putting x minus I epsilon z. And you see now I have put this imaginary part. And let me make a remark about that. So of course, because f is real valued and because this integral is 0, its imaginary part is also 0. So we can state this. The reason I do this is because, curiously, if you don't put this imaginary part, and basically if you take a limit of this expression as epsilon goes to 0, then you end up with nothing. But if you put this imaginary part, and maybe I can explain this later, but if you put this imaginary part and take the limits, then you end up with some localized information at the point r equals 0. So this is actually something, some neat thing that happens in this dimension. Okay, so then we take the imaginary part, we look at this expression, and then what happens is, because this determinant is positive away from 0, then this imaginary part of this expression, you can show that it's less than or equal to c epsilon if you cut away from this point r equals 0. Right? So the imaginary part of this expression is going to be quite small. This is another, maybe this is the key reason actually I'm taking the imaginary part here. Right? But there are also other reasons. So if you take the imaginary part, this expression is small if you move away from 0. On the other hand, if you are near the point 0, then you can actually show that the imaginary part of this expression basically looks like this. Okay, this should be r. This should be r, sorry for that. So you end up with this expression. And now what happens is if you take, so this Jacobi transform is 0 for all epsilon, but because of this fact, basically you can just look at intervals very close to the origin. And then if you just take the limit as epsilon goes to 0, then you see that basically you recover the point value of f at this point. And that this will tell you that f at that 0 must be 0. So f at this arbitrary point P along the geodesic must be equal to 0. And this concludes the proof in that case. So this is how our proofs look in 2 and 3 dimensional manifolds, Riemannian manifolds, and you can repeat the same proofs for Lorentzian manifolds. So an interesting direction that we didn't consider was to, of course, is to consider these Jacobi transforms in higher dimension and invert them there. Another interesting direction would be to remove this conjugacy assumption. So this is something that I believe you can do, in fact, but at the moment that we don't know how to do this at all. But I believe that if you have conjugate points, then what happens is that you should be able to prove that they contribute. So what you can show is not perhaps injectivity, but you should be able to show that some linear combination of f at the point P and the other conjugate points will end up being 0. So this is another direction where these transforms hopefully can be pushed. Okay, so this is what I wanted to talk about. Thank you for listening.
Thank you very much, Ali, for the very nice talk. Thank you very much. Are there any questions or comments?
Can I ask a question, please?
Please, please.
Ali, so just to understand, so in which sense do you improve here your result with Laurie about the recovery of semi-linear term.
This is actually based on that talk. I just gave it.
Oh.
This is just a different spin to that talk. I just wanted to focus on these Jacobi transforms. But so in terms of that result, it's basically something that appears in that work. So you can use these to recover quadratic terms so far in dimensions 2 and 3. But so that is in terms of inverse problems, that is how they can be used. But as I said, it can also be used for, let's say, quasi-linear nonlinearities. But I don't want to focus too much on the inverse problem side, because there might be other ways also, to recover quadratic terms, so there are more complex interactions when you have nonlinearities. So you can always generate more sophisticated dynamics. So I will, yeah.
Okay, so this is part of your work with Laurie?
This is part of that work, yeah.
Okay. Just wanted to understand, because I cannot see the difference. Sorry.
Thank you. Are there any other questions or comments, please? Any questions or comments? Are there any questions or comments, please? Okay, if not, thank you very much, Ali, for the very nice talk. Thank you very much, everyone, for coming. Thank you very much.